Poles and use of Wolfram Alpha.
Hello, I hope you're doing well. I'm Laura Jesus Rodriguez. I'm pursuing my last year's Bachelor of Mathematics with a concentration on secondary education. I'm a student at the PUCMM University on the Santiago campus. PUCMM stands for Modern Teacher Pontifical Catholic University. With this video, I intend to create a useful explanation to anyone interested in learning about series and poles as part of the subject complex variables given by the teacher, Juan Antonio Milané. Hope you enjoy it and learn.
Zeros and poles. Here we have our table of contents. In here we have today's goals, our main goal and specific goals, the main questions that we're gonna answer in this video, keywords, prior knowledge. We also have our main topic, zeros and poles. We'll see an explanation of it, a few examples, and some of the applications of zeros and poles. We're also going to see a graphic proof using the software GeoGebra and also Wolfram Alpha. We're going to prove with softwares our exercises in order to check that they are correct. And we're also going to see some proposed exercises for you guys to practice. We will also have our conclusion, a few quotes of some authors. We're gonna see the tech tools that we used in this video, and finally the bibliographic resources. Alright, so today's goals are, the main ones gonna be determine the number of zeros, poles, the order of the poles, and the residue of a function. And the specific ones are gonna be, we're gonna see a graphic proof of the concept zeros and poles using one of the softwares. We're also gonna show that singular points are poles with exercises. We're gonna get the order of poles and obtain the residue on the exercises too. And then after that, we're gonna prove the results using GeoGebra and Wolfram Alpha. Questions that we will be answering along this video. Okay, so our first question is, what are zeros and poles in complex variables? What are their types? The second question that we'll be answering is, how can I express them graphically? And the third one is, what is the residue and why is it useful? And most importantly, how we calculate them. Keywords. Here we have a few terms that we will need to learn or discuss a little. So here are zeros, poles, residue, singularities, Lorentz series, and poles of n order. Prior knowledge. Here are the things that we need to know before we get in touch with the topic zeros and poles. So before we start, we need to know about Lorentz series. We cannot forget them. But what are Lorentz series exactly? We're gonna answer that right now. Lorentz series. So before we even talk about Lorentz series, we need to know that singularities are what make Lorentz series Lorentz series. What is it exactly? Well, we'll see right now. So if we let C be equals to C sub 0, be an isolated singularity of a certain function, let's call it f of z, then f of z could be represented in the following series. So this is basically the Lorentz series. And here we have the main part of the Lorentz series and the analytic part of the Lorentz series. Okay, so the main part is going to be the one that we're going to focus on, well, later on. And it's the sum that goes from k equals 1 until the infinity of a sub negative constant, let's call that constant k, times, multiplied by c minus c sub 0 and elevated by that same negative constant. So this is the center right here. That's what we call over here our, and well, the C sub 0 is going to be the center over here, but also the singularity, that is highly important. And it's basically, well, this whole expression over here that it means the smaller ratio is going to be, well, less than this center over here, that is the module of C minus the singularity C sub 0, and that's gonna be smaller than the bigger ratio. So basically this Lorentz series converges in this ring. We also have a representation, kind of an illustration of it. So the singularity is gonna be here. It's called the C sub 0, and as we can see, oh, sorry. And as we can see, this singularity has two ratios. So it has this ratio that's over here, that's gonna be the shorter ratio, and this other longer ratio that is over there. So we have this circle. Of course, since it's the center, it will give us what the center of the circumference will be. And this other longer ratio will give us also another circle that is gonna be like it's gonna be the domain over there. And also, if we notice too, we got the curve or the contour over there, and we see that it's simple, that it's closed, that it's a closed curve and simple. I'm giving you this illustration because this Lorentz series and the singularities and the main part and everything else connect us to another new theorem that it's really helpful if we want to give solution to a certain kind of integrals. So yes, before we go into the next slide, we need to discuss a little bit about singularities. We need to learn a little about how can we classify them. And last but not least, we need to be able to identify them and also calculate those singularities given a certain function. As we were talking about before, in the Lorentz series, the whole connection with the singularities and this power series comes to this. So we have a function that it is analytic in a certain domain, okay? But this domain, this is the domain of a ring or a disk, however you want to call it, is defined by this condition. And as we said before, this is the smaller ratio and this is the bigger ratio, and between that we have the module of C minus C sub 0, remembering that C sub 0 is our singularity, and also that C sub 0 is going to be our center as well. As we can see in the illustration, it is the center of our disk over here. And if we got that, well, if we got that condition, then we could say that f, or the function, could be represented in the following series. So we said that it will be represented this way, and it is valid to this sorting condition too. What is very important to know is that in order to use this Lorentz theorem, that it also connects with the integration using contours, and that it is really necessary in order to go over the topic of the Cauchy's residue theorem, is that it also, with the Lorentz series, we got the residue that is symbolized like this with a sub -1, and we also could describe that as a residue of a certain function. And of course, before we even calculate that residue, we need to know the singularity of that specific function. So that's why we got to study all of that. There are even three types of isolated singularities, the poles removable singularities, and the essential singularities. Will be over them on the next slides, and we'll see the importance of this Lorentz theorem and the singularities and how we could take advantage of it. So here we have the types of isolated singularities. Over here we got this Lorentz series, and well, the main part of the Lorentz series. We gotta focus on that for now. Like, it's not that the Lorentz series is not important or the analytic part is not important, but for these cases we will, well, our focus will be on the main part of the Lorentz series. So we have three types of isolated singularities. The first one is removable singularity, as the as the name suggests. The removable singularity is that singularity that can be removed. And we said that if the terms of the sum that goes from k equals 1 until the infinity of a sub minus k over c minus c sub 0, remembering that c sub 0 is the singularity elevated to a certain constant, then we say that we have a removable singularity. Another type of isolated singularity is the pole, okay? So if we got this sum, and it also, we said that if this sum has a finite number of terms, then we say it's a pole. But on the other hand, if that same expression over there has infinite terms, then it's not a pole anymore. It is an essential singularity. Finally, zeros and poles. So, what are zeros and poles exactly? Do they have anything to do with this game that's called Marco Polo? Do they have anything to do with the number 0? Or, like, they have anything to do with this game called tic-tac-toe? So, how can we see zeros and poles graphically? Well, a quite simple description could be this one, or representation could be this one. We got to remember that when we are working with the complex numbers, where we're working with the complex plane as well. So there's going to be a ray that's going to be a real, and there's going to be another ray called y that's going to be representing the imaginary numbers along that axis. So here, if we're talking about a 0 and we say, okay, so -1, the point -1 is a 0. So we go until that point and we draw a little circle over there. If we said that the number 3 is a pole, then we draw an X or a little X or however you want to call it. We draw this inside of that. Well, yeah, kind of like up that number. So that's a simple way to do that, to represent them, to classify one from the other. It's quite simple, but there are other ways as well that we're gonna see along the video. So here we have a few examples of zeros and poles. The first one, we have the function, the following function, and we said that in this case we're gonna see in which points my function won't be defined. And in this case, those specific points are plus and minus 1. We could see that if we even like substitute in it. And so we said we have zeros of order 1 in this case. So we got this other function that is sim pi n. In this one we gotta differentiate a little so we could get a clearer vision. After we differentiate, we will get the following result. So the derivative is pi times cos pi. So as we see when we got the cosine, then our function will never like not be it doesn't matter the integer exactly, my function won't vanish at all. So even if sine is still there, since our cosine, if it's for example the cosine of 0 is going to be 1, so it will never really disappear. Function c cubic minus 1, and all of that is going to be elevated to 3. So we can see that these are zeros of order 3, as we notice here, at z equals 1 and at c equals e elevated to plus minus 2 pi I divided by 3. So we basically did the same over here. We noticed that even if it's a function and okay has that certain denominator, the result will still be the same, just that in this case, instead of being just a 0, it's going to be a pole of order 1. There's the difference over there. So right now we're going to see poles exactly with these examples, just so you could kind of see the difference between one and the other. So we also have this function that is the sin of pi z, and divided by this expression. We said that it has a pole of order 2 at c equals 1 and a pole of order 3 at c equals e elevated to plus minus 2 pi I divided by 3. In this case, we gotta really pay close attention to the product here, because at first we'll get a pole of a certain order, and then we'll get another product that will give us another order. So in order to not get confused at it, it's really, we gotta be careful with the function. And let's see, this is the last example. So we have this expression, and as the other one that we saw before, instead of this being called a 0, we can see that it is in the denominator. So this is a pole. So we have the pole of order 3 at c equals 1 and the pole of order 3 at c equals e elevated to plus minus 2 pi I divided by 3. This is our first exercise, and it says, show that the point z equals 0 is a simple pole of the function f of z equals to the cosecant of z, that is equals to 1 over the sin of z. And besides that, we're gonna also gonna do that the residue there is unity by appealing to A and V. A is the theorem 2 in section 69, and V is the Lorentz series for the cosecant of z that was found in the exercise 2 of the section 61. In order to give you guys some context about the theorems that the book says, specifically, we got the theorem number 2 that it says let two functions p and q be analytic at a point c sub 0 if p of c sub 0 is different of 0. Same happens with the derivative of q c sub 0, and q of c sub 0 is equals to 0. Remembering that c sub 0, well, it's gonna be, yeah, oh, the same theorem says, that c sub 0 is a simple pole of the quotient then of P of Z divided by Q of Z. And we also got that the residue of C equals to C sub 0, then of that quotient then will be equals to P of C sub 0 and the derivative of Q times C sub 0. And then we got the number 2 part that it says that by writing the cosecant of Z equals 1 over sin of Z, and then using division we show this, that this is true, and it says that the cosecant of Z is equals to the sum. So let's solve this problem. So the first thing that we have is that the cosecant of C is equals to 1 over the sin of C. So since we got that, we can rewrite this. We can use the expression that is written right here, that it says P of Z over Q of Z. We can totally use that. That's why we rewrite the cosecant of Z. This could be validated by this. So we know that P of Z is equals to 1 since it's the numerator, and Q of Z it's equals to the sin of Z since it's the denominator of our expression. So now that we know that, since P of 0 is equals to 1, that means it's different of 0, and we also know that Q of 0 is equals to sin of 0, which is also equals to 0. And finally, the derivative of Q on 0 is equals to the cosine of 0, that it's equals to 1, that is different of 0. Then we can say that Z is equals to 0, because there must be a simple pole of the cosecant of Z with the following residue. And we said that since according to the whole process that we did, we can say that the residue is going to be 1 over 1, that is equals to 1, as we were trying to show before, that what the exercise told us. So right now we're gonna do the part B, that it says that the first thing that we know is that the cosecant of C is equals to 1 over C plus 1 of 3 notation of C plus this over here, and with this condition that the modulo of C is between 0 and pi. We know that from the exercise 2 of the section 61. So since the coefficient of 1 over C here is 1, as we can see, then it follows that Z is equals to 0, since it's a simple pole of cosecant of C, and the residue is going to be 1. For our second exercise, we're going to show that this whole expression, when we got the residue of C equals pi I, it's going to be, well, through this specific function, that is C minus the hyperbolic sin of Z over the quadratic C times the hyperbolic sin of Z, that is equals to I over pi, and that the sum of, well, the sum of the residue, that when Z is equals to pi I of this certain expression, plus the residue of C equals negative pi I of this expression, is going to be equals to negative 2 cosine of pi times t. So the first thing that we do is that we write the expression as we are used to right now. This is the numerator and this is the denominator. So we specify that. So far we're clear with this. Then the next step that we do is that since P of pi I is equals to pi I, that is different to 0, and since Q of pi I it's equals to 0, and finally the derivative of Q in pi I it's equals to pi, which is also different to 0, then we could basically just substitute and see that the residue of this following function evaluated at c equals pi I, it's gonna be equals to I over pi. Okay, so for this exercise, the first thing that we're gonna do is write in the expression as it follows. So we got that the exponential of c of t divided by the hyperbolic sin of c is going to be equals to p times z divided by q of z. And as you see, this is the numerator right here, so this will be equals to x of z times c. And since this is the denominator, we're going to see that this is the hyperbolic sin of z. So later on, we could see that if we substitute following this rule, the one that we saw before on the last exercise, and then we will see that p of pi I divided by the derivative of q of pi I is going to be equals to negative x of pi t. And since this is what happens when the residue is z equals pi I, then if the residue is equals to negative pi I, then this is what we're gonna get, negative and this expression. So it's quite easy to show. This is quite easy. Finally, since what they wanted us to do was to sum these two expressions together, when we finally simplify this a little, these two expressions, we will see that we will get finally negative 2 times the cosine of pi t.
So here we have this exercise. Well, we're going to check that the exercise that we did before was correct. So we're going to go to WOLFRAMALPHA and we're going to write poles of and the certain function that we want to see and what are the specific poles there. So when we do that, we're going to see that there's even a graphic representation of it. We can see that 0 is one of those simple poles there. And with the other exercise that we got, that it says that to find the residue of this function at z equals pi I, then when we do that, when we enter, then we're going to get through WOLFRAMALPHA, that's going to be I over pi, just the way we did it.
So we're gonna do the following exercise, and it says, find the residue of the function f of z equals to c divided by c squared plus 1. And we're gonna find the residue at these 2 points, at c equals I and at c equals negative I. So we're gonna first find this residue, and by that we're gonna get the following. So the residue of c equals I of this following function, then it's going to be equals to the theorem that we saw before, that we proved before, and taking into account that p is going to be the numerator and the derivative of q is going to be the denominator, then we're going to get that, considering that c is equals to I, p of I divided by the derivative of I is going to be equals to I over 2I, as we see. And by simplifying, we get that the residue of c equals I of this function is going to be equals to 1 over 2. So if we want to know what the residue of this function at c equals negative I is going to be, then therefore, if we consider the same theorem and just by substituting the c with negative I in this case, we're going to get that this is going to be equal to negative I over 2 times negative I. By simplifying, we're going to get 1 over 2. Now we're going to prove that with the software WOLFRAMALPHA. So in order to verify that our result was correct, we're going to go to the software called WOLFRAMALPHA, and we're going to write right here our expression. We're going to type residue of our function at c equals I.
after we do that, sorry, we're gonna press enter, and then we're gonna see that the residue of this function at that certain point is gonna be 1/2. And the same we're gonna do with the others, okay? So it's basically more of the same. We just type in residue of and the so-called function, and then we put a specific point that the exercise is telling us. So after that, we're gonna see the same with the other exercise. These exercises are quite similar. Oh, this one is the same. I just evaluated, or well, check if what was the residue at -I, but if we check that, then it's gonna be this 1/2. It's the same. So and again, for this exercise, that it's quite similar to the other, we're asked to find the residue of this function at each of its poles. So the first thing that we need to know is, like, we need to find the poles first. So once we know that, what are those poles? In this case, the poles of this function are -1 plus 2i and -1 -2i. So once we know that, we actually now have our residue of c equals to -1 plus 2i. There's one of the poles. And also we got the residue of -1 -2i. And when we finally follow the same steps that we have done so far, we will get that the residue of these two functions will be 1/2 minus I/4. Then here, if we look for the poles of our function, we're gonna get that those poles are these two simple poles. And even if we didn't type there the residue, the same software is gonna give us the residue right here. They will tell us what is it. And right here, they will also give us the graphic, as we see before. They'll tell us that, remember that what we were discussing earlier, that we symbolize the 0 with this little circle and the poles with the little x. So we find that this is the pole, sorry, the 0, and this is the... Okay, since we have practiced all that, why don't you try this 2 exercise? Now, with the help of some softwares, specifically GeoGebra and WOLFRAMALPHA, we're gonna prove our answers. Now, let's check this using WOLFRAMALPHA. So, in order to verify that our result was correct, we're gonna go to the software called WOLFRAMALPHA, and we're gonna write right here our expression. We're gonna type residue of our function at c equals I. After we do that, sorry, we're gonna press enter, and then we're gonna see that the residue of this function at that certain point is gonna be 1/2. And the same we're gonna do with the others, okay? So it's basically more of the same. We just type in residue of and the so-called function, and then we put a specific point that the exercise is telling us. So after that, we're gonna see the same with the other exercise. These exercises are quite similar. Oh, this one is the same. I just evaluated, or well, check if what was the residue at -I, but if we check that, then it's gonna be this 1/2. It's the same. So Then here, if we look for the poles of our function, we're gonna get that those poles are these two simple poles. And even if we didn't type there the residue, the same software is gonna give us the residue right here. They will tell us what is it. And right here, they will also give us the graphic, as we see before. They'll tell us that, remember that what we were discussing earlier, that we symbolize the 0 with this little circle and the poles with the little x. So we find that this is the pole, sorry, the 0, and this is the pole. So the same goes with this other exercise. It's more of the same. It's even kind of boring, especially if the exercises are quite similar. So we're just gonna find the residues of this function at c equals pi over 2, and then we'll find that the residue it's equals to -1. There we go. And the last one is we're gonna check the residue of this function at c equals 0. So when we do that, we'll see that the residue of that function is going to be equals to 3 over 10. So far, we have seen that all of our answers were correct. In case you are a little confused with a process that you did, you can always check with this type of software, such as WOLFRAMALPHA. They're very helpful. I do recommend you to use it. I think it's really useful and it will help you to see things clearer once you check your operation there. Okay, so we will give you this little challenge for homework. You should try to do this one and see what you get. All right, so we will let the contour of n denote the positively oriented boundary of the square whose edges lie along the following lines. In this case, the n is a positive integer, so we gotta show this, that this is true, that this condition is true. And then we're gonna use the fact that the value of this integral tends to 0 as n tends to infinity, which is pointed out in the exercise 7 of the section 41, and it follows that this is what it has. So checking that suggestion that we had on the last exercise, it says that we're gonna use the fact that the value of this integral tends to 0 as n tends to infinity according to this exercise itself. Here we have the simple closed contour and it's as shown. So I got this square. It has different singularities over here on pi, on 0, negative pi, and also on the negative n terms of, well, times pi, and also n terms times pi. We also get this specific points n plus 1 over 2 times pi, and we get this curve that is closed and that is simple and that it follows this orientation. So then we see that when with this contour we got this also this function that has isolated points, or well, isolated singularities. Over here we can see them. These are specific poles, but there's a pole at 0, at pi, and negative pi, and at these points too. So to find, in this case, the residue at c equals 0, we use the Lorentz series for the cosecant. the cosecant of c that was found in this exercise specifically. So we find that here we have this expression all along, and once we do that, then we can, according to this, the module of z has to be between 0 and pi. My bad. So this is the expression that we get from that. Next thing we're gonna do is that in this function we see that we got a pole of 43 at z equals 0, and that pole is 1/6. Then for this point that are z equals plus minus n times pi, where n is equals to, well, natural numbers, specifically 1, 2, blah blah. We write this expression as we have seen before, 1/z quadratic times the sin of c, with obviously this is the numerator and this is the denominator. Then we notice that in this case there is this certain condition where we're working with plus, minus, and pi, and these are the conditions that are given by that. So when we want to find that residue at that certain point, we just gotta do the following. So we multiply by -1 over elevated by n in the numerator and in the denominator, and we got this result in the end. So by the residue theorem, we got this. This is the integral of a contour, a contour integral of 1 over, the function given, and that's gonna be equals to 2 pi I times 1/6 plus 2, the sum of n equals 1 until n, and the expression that we got by calculating the residue when z is equals to plus minus n pi. Finally, when we rewrite the equation in this form, we get that it's equals to pi quadratic over 12 minus pi over 4i. This is the integral, the contour integral of our function, and then we're gonna get that if we follow this exercise, the one that they advise us to use, we see that the value of the integral tends to 0 as n tends to infinity, and we finally will get this sum formula. And that's it.
Now we're gonna see if, okay, now with the software Wolfram Alpha, we're gonna check the poles of this specific function, and when we enter it, we're gonna get that the poles are c equals 0 and the residue is equals to 1/6. We also got this graphic over here showing us the pole over there.
Okay, but how can we see them in a graphic? How are they represented? That's what we're gonna see right now with the software GeoGebra. Let's use GeoGebra to check this. Here in GeoGebra, we have this kind of representation according to the past exercises. So in here we have this circumference. In this case, this circumference was given by the other exercise, and we kind of see how it might look since this circumference accomplishes the definition of the exercise that we were given to. And it also has a direction. This is the direction that it takes with this attempt of an arrow. So when we want to see poles and zeros more specifically, what we do is that we use these symbols. We use an X if there is a pole, and we use these little circles if there is a zero. So in the other exercise that we had, we need to basically sketch this
this figure that is over here. And in the points where there was a pole, then we will put the x's. If there were any zeros in this figure, then we will put circles over there. That is basically how we manage to identify one from the other.
Okay, so before we start, the functions that were used here are specifically three, as you might notice. So the first one is the impulse function, the second one is the step function, and the last one is the sing-t function. So an impulse function is basically, as the name says, sorry, a very short pulse. It is infinitely short, theoretically, and it is used to evaluate system dynamics. Okay, so in the real world, an impulse function is basically a pulse that is too short, is much shorter than the time response of the system, basically. And we also got this step function. It's also called a staircase function because of the way it kind of looks like it's similar to a staircase. And it is defined as a piecewise constant function that has only a finite number of pieces. So in other words, it is a function on the real numbers that can be described as a finite linear combination of indicator functions of given intervals. And well, last but not least, the sing of t, but we already know that one. But these two are really quite interesting and are very useful in this type of representations.
All right, so here we have this animation that was inspired by the author Adam Becker on MATLAB, who has one of these animations as well. So we can see that this shows the time response of a signal, and it's represented by poles and zeros. And all the poles and zeros basically can be moved like this, and they will have a direct effect on the domain here. We can see how the graph changes gradually. And also, we call the system a stable system if all the poles are in the open left hand plane. We can see how the zeros and poles can be applied in other fields as well. And what happens if the system is unstable then? Well, if even one pole is in the right hand plane, the system will grow infinitely, right? So when that happens, we can call this system an unstable system. Yes. So basically, it's not even like I mean, we don't only use series and poles like in order to find residues or anything like that. We can also see them on other fields as well. They have other applications as well. Alright, so here we see that poles are represented with X marks and zeros are represented with tiny circles. So this is a really simple representation of series and poles graphically, but there are many ways to really show them or see them. So we're gonna see a few of those. So here we have another representation. In here we get that right here, like in this floor down below, we could see that we have our zeros that are the tiny circles and our poles represented by the tiny x's. So we can see that when we have zeros over here, this is what happens to our specific function. It goes like this, goes down. And when we have poles, then it's like if we got kind of mountains. They look like mountains over here, and they have like a little hole there. So we said that the poles here, we said that the poles here are kind of holding the surface just like a real life pole might do. That's why they're called like that. And this is another way, like right here, right down, we see that there are also other lines, or well, kind of curves right here. We can also see those same series and poles on our imaginary plane, or well, our complex plane, and with those colorful curves around them. So this is another example, well, more of an application. They first did these two poles, and after that they represented like this and also like this, so that they will see clearer in the function like what is going on. These kind of examples are really good once we want to practice visually of what is really going on with my function.
Alright, so these are the functions of these three phase portraits. In these two particular cases, what happened was that in this case, the function was smashed and they basically used code to smash it so that they could represent it like this and see, well, each of their poles. And later on, with this one, that is the essential singularity, they took this function, and what they did was, they just squashed this function again using some kind of code at MATLAB, and basically use a transformation to see a little bit of the function. So yeah, that was before the explanation. I wanted to make it clear.
This is another way to represent series and poles. Here we have three special cases: when we have a removable singularity, when we have poles, and when we have an essential singularity. So these representations are called phase portraits. So these colorful guys will kind of show us how we could represent series, poles, and other singularities as well. So here in the first picture we have a removable singularity, and we could basically see that the picture itself stays really quiet. It barely changes really. So even though there are two things over here moving, in the case of that function, those are not singularities, those are zeros, and are specifically negative pi and positive pi, so they are not specifically like a singularity. If the case was that instead of being a removable singularity, it were a singularity or a zero or a pole, then we will have something like this. We will see how the colors are kind of mixing, kind of moving like this. When it comes to poles, this is exactly the case. We have 4 poles in this image. So, okay, sorry. So, and when it comes to poles, this is the case. And finally, when we're talking about an essential singularity, then we could see how the colors appear infinitely many times. So that is when we have an essential singularity. Just one.
In case you want to keep looking at this type of representations, I do recommend you the website, or well, program Wolfram Mathematica or Wolfram Alpha. We could see different representations of zeros and poles and other singularities. In this way, we could also see another type of representations over here, and many resources as well. The Riemann sphere, for example. So I do recommend you to check this really powerful site. Again, there are many tools that can be used, and I do recommend you to visit.
Applications of series and poles. So, The series and poles are really useful especially if we're talking about theorems such as Cauchy's residue theorem. If we want to find a residue, we need to know about series and poles, and especially we need to know about or how to identify this type of singularities. If we don't, then we're gonna have a few problems there. We're gonna struggle a little, especially if we're trying to um, solve problems related to the Cauchy's residue theorem. So they are important. At first, it might be like, okay, but they're so easy. Like, why, why are we going to dedicate or spend a whole chapter of just series impulse? It is highly important because if we don't know about Lorentz series, and if we don't really handle those concepts, and if we don't identify them, we will have a lot of problems at calculating and also at finding the things that are being asked to us. So basically, it's that. They can also be really useful when we are working with contour integrals as well, and especially when we're working with other fields. I mean, if we want to see or if we want to make sure that a system is stable or not, poles and zeros are used. Then later on we'll see a little bit of it. But zeros, poles, singularities, more specifically, are way important and have many applications out there. Proposed exercises. Here we're gonna practice a little with these ones. Well, you guys are gonna practice with them. Now, let's practice. Here are the exercises, and see that here below are the answers of these two. On the following exercises, you gotta analyze a little bit more though. So here we have exercise 3 and 4. We have to determine the order of the pole at z equals 0 for these two functions. And last, we have these two other exercises. It says, the number 5 says, find all singularities for the following functions, describe their nature. So we have these 3 functions for you to analyze, find the singularities, and describe the way they tend to be. So here we have the last exercise that says classify which of these singularities are poles. If they're poles, then you gotta tell what is the order of that pole. You also gotta classify if there's a removable singularity and if there is an essential singularity. In conclusion, last reminders. Okay, these are things that are very important and that we shouldn't forget, because if we do, then we might struggle when we do exercises. So these definitions need to be taken apart, and this is the basically a little summary of what we have seen so far. So we cannot forget about Lorentz series. We cannot forget about the main part of the Lorentz series. We need to know, well, remember that a 0 is a value of c that makes the function f of c be equal to 0, or be expressed this way. A pole is a 0 of the denominator of f of c that makes that f of c is equals to h of c divided by 0, with h of c different of 0, okay? So a removable singularity, it's, as the name says, a singularity that can be removed by using this following formula. We need to keep in mind the essential singularity too, that when we are operated with the Lorentz series, then by using the main part of it, when we see that there are infinite terms, then we know we have a essential singularity right there. And last but not least, we got the residue. We need to know exactly what is the residue and how we calculate it, how we know what is it about. So in this case, the residue of a certain function, then we said that is okay, the residue of a certain function of f, or a certain function, this is just a symbol to refer to a function at c, let c be like a constant, is the coefficient this a sub 8 sub negative 1 sub 0. Okay, so this is basically the way we represented our residue, and it is there in the Lorentz series of c minus c elevated to -1. This is basically like the center of it in the Lorentz series expansion of f around c. Alright, so here are a few quotes. The first one is, "When you get tired, learn to rest, not quit." That's from Bansky. Bansky is a street artist whose identity remains unknown. In the late 90s, his provocative stenciled pieces gathered a lot of attention. He directed the 2010 documentary called Exit Through the Gift Shop. And this quote basically is telling us that no matter how hard things could get, there's always have to be a certain kind of motivation or something that pushes us to keep going even though things get hard. We just have to take a break, but we cannot just give up on our dreams if we want to accomplish them. The second quote is from Einstein, and it says, "I have no special talent, I am only passionately curious." This one really got my attention because sometimes we think that in order to succeed or to somehow be special or really known by others, we need to have this like super awesome qualities, and that is not necessarily the case. Sometimes you just are very curious about things, and once you want to know about those things, you start to do your research or ask questions and really like get into that certain topic that is calling your attention. So yeah, doesn't have to do with having some kind of special talent or anything. You're just having a lot of passion for something and you just want to keep going and keep learning about it. Oh, and Einstein was a German physicist who is considered the most important and popular scientist of the 28th century. And he's also known for the theory of relativity. And finally, the last quote says, "Don't let yesterday take up too much of today." This one's from Will Rogers, and it's basically saying that we cannot live in the past. We need to face the things that are not going the way we plan and not just feel sad or angry that we cannot change those things or that there's nothing that we can do about them to change. We just need to keep looking forward and give the best of us. William Rogers was an American actor, performer, and humorous social commentator. He made 71 films and wrote more than 4,000 nationally syndicated newspaper columns. Okay, so here we have the tech tools used in this video. As you can see, this is a PowerPoint presentation. I took this template from the website Slidesgo. The softwares used in this video are GeoGebra and WOLFRAMALPHA, and some of the illustrations are from sites like Brilliant and Canva.
I'm Laura Abril de Jesus Espinal Rodriguez. I'm currently studying in Mother and Teacher Pontifical Catholic University, or PUCMM, Santiago campus, to get my bachelor in secondary mathematics education. Thank you so much for watching this video. Here are the bibliographic references. For this video, I used the first course of Complex Analysis with Applications by Seal and Shanahan, the second edition from 2011. And I also used two versions of this book, the 5th edition and the 7th edition of the book Complex Variables with Applications by Churchill and Brown, the one from 1986 and the one from 2004. These books can be found on Amazon, and they can also be found under specific publishers. The one that's from Seal and Shanahan could be found on Sandwich Learning Editors, and these two could be found on McGraw-Hill Inter-American, Spain. I also worked with these two books. This one from Hoey, 2003, is called Complex Analysis, the Springer series. And this one that's called Mathematical Methods for Engineers and Scientists 1, that is from the author Tang from 2007. Both of these can be found on Springer.
Thank you so much.